projector on. Okay, we are now recording. Let's get from the current slide, and we're ready to go. Don't know of many announcements. I guess there's one sort of a good news, bad news situation. The bad news is next week, 4th of July is on a Wednesday in the middle of the week. That means there's no school on Wednesday. That's the sad news. The good news is, though, it won't affect this class any. We meet both days. All right, good. I knew I could make you happy. All right. So, oh, I forgot to mark you here. Let me do that before I forget about it. James. Okay. This here. Okay. Guess we're ready to go. Any questions on anything we've covered so far? Okay. Now, I don't know if you remember. I know right at the end of the period, I was rushing, and we were moving through things pretty quickly. But here was the deal, and those writing out the equations and the various things we had, we saw, I hope we saw this, that if we started with a function with a matrix here, okay, and what we're multiplying by turned out to be kind of like an identity matrix here. Well, if we solve those simultaneously, basically what we're doing is getting this into an identity matrix, and then what we wound up with here turned out being the inverse of the matrix that you started with. That was the point. That was the thing. So that leads us to our finding the inverse of a matrix by Gauss-Jordan elimination. And basically, this is one of the main reasons we use Gauss-Jordan elimination, because it does get us back into, just Gauss elimination just gives us, we're going to give it a name later, in fact, fairly soon. It just has zeros below the diagonal. The diagonal will be mostly ones, zeros below it, and then you back substitute. Gauss-Jordan elimination gives you one on the diagonals, zeros above and below the ones, and that's what we want to give you an identity matrix. So that's why we use Gauss-Jordan elimination for this. So finding the inverse of a matrix by the Gauss-Jordan elimination. Now first and foremost, if a matrix is not square, it does not have an inverse. No, but that doesn't mean that all square matrices have inverses. They don't. Some of them just don't. But no rectangular matrix will ever have an inverse. It has to be a square matrix. Okay? So the first thing is a square matrix. Okay? Of order n. Which means n by n. Okay? N rows, n columns. Okay. First thing you do. Write the n by 2n matrix, which is matrix A augmented with matrix I sub n. Okay? Now, matrix A is an n by n, and certainly it's the identity matrix of that same size is going to be squared, okay, and it will be n by n. So you write that as that. So it'll be an n by 2n. The n rows, but twice as many columns. So you have the square matrix A here and the identity matrix of the same size there. So that's why it's 2 columns. So write that on the left of the identity matrix on the right, and they don't put the bar in between, so I'll take it out. That means partitioned. They don't use that now, even though they did earlier at some point, but that's the matrix. And that's called the adjoining the matrix I to the matrix J. And that's what I said. The adjoining those two matrices together. That's where I use that. Now, later, next chapter, we're going to talk about the adjoint of a matrix, which isn't the same as adjoining the matrices. So it's we use two terms that are very similar to each other. We're not going to worry about it now. Okay. Secondly, if possible, row reduce A with I. You're doing it at the same time. But the A part is going to hopefully get to be an I as well, an I sub n. When you row reduce, you want the first entry to be a 1, zeros below it. Next, first of it, non-zero entry in row 2 would be a 1 with the zeros above and below. First non-zero entry in row 3 to be a 1 with the zeros above and below. Basically what you're doing with row reduction is getting that matrix A to be an identity matrix. Okay? But you're doing the same thing to the I's. You're doing all those steps that you're doing to make this A into an I, you're changing the I. Every step changes the I. So it's no longer an identity matrix. Okay? But you do it on the entire matrix AI. Okay? I like this line between them, they don't. Okay? And what you get at the end is a matrix that looks like this. I, A inverse. Okay? Now we already defined what A inverse is. If that's not possible, if when you're going along doing a row reduction on A and you wind up with a row of zeros at the bottom, or you skip a column before you get your next non-zero entry, and you can't get that to be an I, then that matrix A is non-reducible. It's a singular matrix. Okay? So it happens sometimes. Even with the square matrices, they just won't have an inverse. Okay? Now, third step, and I don't know many people who do this, really a good idea to check your work by seeing if A times A inverse is equal to I, then check it the other way and make sure that A inverse times A is also equal to I. Okay? If both of those are true, you know you've got the inverse. Frankly, when you get it there, we usually stop there and say that's the inverse. Okay. Most of the time you don't go back and check, but it's a really good idea to. Okay? Now, there's another linear algebra applied at the bottom of that page 64, and it's dealing with Hooke's law. Okay? And that basically was, you think of it in terms of springs, but it doesn't have to be springs. Anything that when you perturb it, does it come back to its original shape? Okay? For instance, I press on the board. I don't know if you noticed, but it did move in some, but then it popped right back. So I did a force, and I created a distortion, but when I released it, it came back. That's sort of obeying Hooke's law. I can press on the concrete all I want. I can't tell I'm distorting that any. But if it, yeah, okay. Yeah, this is plastic. I can do that. It comes back to the original shape. Okay. This is metal. I'm probably doing a little something to that. I can if I do it that way. Just about anything responds to something like that, including, and basically we call any object that comes back to its original shape an elastic object. Okay? The metal, the plastic is elastic if it comes back to its original shape. Now I can easily imagine, I'm not going to do it, but putting my hand through the board hard enough And I think someone did that, not their hand, they just dropped the board and cracked it. Well, that was no longer elastic. You passed what they call the elastic limit then. This plastic here, I know that if I poke that with something sharp enough, it's not going to come back. It's going to either dent or break. Okay? That would be past its elastic limit. But as long as you're within that elastic limit, your deflection or distortion is related to the force that you applied by some constant F. And that's called the flexibility matrix. Okay? And F inverse would then be the stiffness matrix. Okay? So you get the concept there. One is how flexible it is. The inverse of it is how stiff it is. Okay? Now, are you an engineer by any? What are you studying for?
Computer science.
Second? Computer science. Okay. Boy. I bet you do some stuff with, or at some point we'll probably do some stuff with encryption. Okay. And for anything you encrypt, you also have to have a code to unencrypt. Otherwise you can't read it or you can't hear it and understand it. Those would be similar. I bet you're involved with inverse matrices when you're doing something like that. So it's right down your alley, whether you realize it or not. And Lauren's back. Okay. Or more. Okay. Okay. So anyway, that is one type. Another in electrical. That's why I asked. I thought maybe you're an electrical engineer. In electrical circuitries, we talk about resistance as the basically the resistance of a material to have current flowing through it, whereas conductance is the ease by which current flows through a material. Those would be inverses of each other. Okay, so we run into those kind of things all the time, and when you're dealing with multiple dimensions, you're going to be dealing with matrices. Okay, too much on that probably. Let's do example 3, which is a far simpler thing than talking about the others. Okay, so find the inverse of this matrix. Here's matrix A. 1, -1. Ooh, goodness, that was a -1, 0. 1, 0, -1. And -6, 2, 3. Okay? Now, rather than writing it down again, what would I do?
Add the ones and the zeros.
Okay, and what would that be? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? I've augmented or adjoined the identity matrix to our original matrix A. So what we have now is AI. Okay? That's not artificial intelligence, by the way. Okay? All right. So what's your first step? What's the first thing you want to happen?
1 in the upper left.
And we got it already. We didn't have to do a thing. And what do we want after that? 0 underneath it. How do we make that happen? Say it.
Row 1 and row 2.
Not add them. It'd be row 2 minus row 1. That will give us a 0 in row 2, right? Okay. So this will lead to, since we're using row 1, leave it alone. Write it down. 1, -1, 0, 1, 0, 0. Okay. New row 2 would be 0, 1. That's great. -1, -1 again, 1 and 0. All right. What's the next thing we want to happen? Under that one too. Okay. And what are we going to need to do to make that happen?
Multiply by 6.
Okay. Row 3 added to row 6 times row 1, right? That'll do it, right? So let's do it. 0. -4. 3, you're right. 6. 0. 1. Perfect. Y'all are good. What's the next thing we want to happen? We got a 1 in the upper left, 0 below it. Next one we want, the first non-zero entry in row 2, we want to be a 1. Yes, it is already. So what do we want to happen after that?
Zeros on the top and bottom of it.
Exactly. Okay, so let's start with the top. How do we make that a 0? How do we make that happen? Say that again. That's it. Row 2 plus row 1. And that will do it for us. Let's see if I can squeeze it in here. Got to write a lot smaller than I did before. So we're using the middle row, so I'm going to write it down. 0, 1, -1, -1, 1, and 0. Okay? The new top row will be new top row will be 1, 0, -1, 0, 1, 0. Excellent. Okay, what's the next thing we want to happen? Okay, underneath that leading 1 we want a 0, and how are we going to make that happen? Plus 2. Yeah, the one with the leading 1 in it. Okay, got it? Okay, row 3 plus 4 times row 2. All right, first entry will be 0. Second entry will be 0. I read my subscript wrong. Next will be -1. Next will be 2. Next will be 4. And last will be 1. All right. So far, so good. We have a first upper left, we have a 1, 0 below it. There's row 2, first non-zero entry is a 1, 0 is above and below it. What's the next thing we want to happen?
Come on, Gauss elimination.
Okay, not quite yet. Next thing we want to happen is the first non-zero entry in row 3 to be a
Positive
1, and it's a -1. So how do we make that into a positive 1?
Just multiply by.
Multiply everything in the row by -1, right? So I'm going to do that in one fell swoop here, a few. That would be a -0, which is 0, -0, which is 0. That will become a +1, a -2, a -4, and a -1, right? So that was not hard to do at all. I said what I was going to do. It's minus row 3 becomes the new row 3. Okay, we just negated everything in the row. All right, what's the next thing we want to happen? Zero's above it. So in the first row we want a 0. How are we going to make that a 0? How? Second? We want that -1 to become a 0. How do we make that happen? Using row 3. row 1 plus row 3 should do it. So what do we have? Our next one here, we're using row 3, 0, 0, 1. And by the way, we're not going to do a thing to change row 3. That's exactly like we want it. And then we have a -2, -4, -1. I guarantee you that's the last row of our inverse matrix. Whether you realize it or not, that's it. Okay? So what will be your new row 1? 1, 0, 0, -2, -3, -1. Perfect. Now, what do we want to happen in row 2? Okay, again, row 2 plus row 3. Okay, and that should do it for us. And what will that be? 0, 1, 0, -3, it's a 1 above it, -3, -1. It's really interesting. That last row never changed, and they all wound up being the same. All right? Now, from what? If we did it right, sure enough, this is a identity matrix, and this should be a inverse. Now, I hate to do this and take class time, but let's multiply A by A inverse and make sure we do get, what should we get as an answer? Multiply A by A inverse. Okay.
What we started with?
No, we're starting with A. Okay, we're going to multiply that A by A inverse, and we shouldn't get A again. You should get the what? Okay, this is the inverse. When we multiply A times the inverse, what should we get? Yes, the identity matrix I. Okay, let's see if we do. And I hate it. This is a 3 by 3, but let's see. So that's going to be 1 minus 1, 0. Such a pain in the neck. 1, 0 minus 1. -6, 2, 3. And we're going to multiply that by -2, -3, -1. Now, it's fairly seldom that they all turn out being negative. This is almost a little suspicious. -3, -3, -1, and especially since the third rows, our columns are all identical. -2, -4, -1. Let's see what happens. Can we even multiply those two together? Yay or nay?
Yeah.
Sure. What's going to be the size of our result? 3 by 3, because it's 3 by 3 by 3 by 3. The middle threes are the same, so you can multiply them. You're left with 3 by 3. So 1, 2, 3, 1, 2, 3, and 1, 2, 3. Okay? Let's start with 1, 1, and what do you get? A little louder?
It's the first row times
First column, yeah. Column out. First row by first column.
So that's -2.
-2.
Positive 4.
No, positive 3.
Positive 3.
So that would be a +1, right?
That's 0.
0. So you get a 1. So far, so good. But we've only just begun. Want to do 1, 2 next?
Sure.
Okay, first row, second column.
It's -3. That's positive 3.
That adds to
0.
0 plus.
That's 0.
and that's 0. Well, so far so good. 1, 3 next. Okay.
Let's see. Positive 1.
That adds to
0.
plus.
0.
Hey, first row did quite nicely. Want to do 2, 1 now? Second row, first column. That adds a 0 too. Hey, this isn't doing too badly, is it? Whoops. All right. Second row, second column.
3, -3, 0, and 4. That's 1.
1. All right. I was first worried until I realized where we were. That's what we want. Okay. 2, 3. Second row, third column.
0.
That's 0 also. Hey, 2 out of 3 rows are okay. How about that last one? 3, 1. Third row, first column.
I can't see it now. Follow.
Oh, I'm sorry.
That's positive 12.
Okay. Yeah. Well,
That's negative 6.
okay, that would be a positive 6.
3 times 2 is negative 2, negative 6.
That goes to 0 again. All right. Let's see how the next one does. Third row, second column.
Negative 18. Oh, positive 18.
Positive 18.
And that is negative 6.
That would be a
That would be negative 12.
positive 12.
Positive.
Positive 18. Yeah. Positive 12.
Negative 6. Oh, I'm sorry. 3 times 4. 3 times negative 4 is negative 12.
Yeah. And that adds a 0. Right? Hey! Can we be so lucky? 3, 3. Third row, third column.
6.
6.
6 plus a negative 2 would be positive. Would be 4.
4.
And 3 times negative 1 would be negative 3, so you get 1.
1. Yes, yes, yes. So sure enough, we did. Okay, I'm going to pull math professor on you. And you really should do the reverse of them, but I'll leave that for the students. Okay? Don't you think you hate it when they do that? We'll leave that for the students. Okay. If you reverse the order, I'm convinced you're still going to get an identity matrix. So yes, we think we found an inverse. And again, don't expect all inverses to be all negative. This one just happened to be. Negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, negative 1. Okay. Now, they show on the side here a online technology guide, and it's actually tied in with what they call Cengage Brain. They keep coming up with these different really clever little titles here. And supposedly it has the program in it that you can actually do these much easier than by hand. But they're so much fun to do by hand, aren't they? Okay. Let's move on before you answer that question. Okay. So let's come down here. All right, to erase? All right, and we'll do example 4. Here's a matrix A, and that's 1, 2, 0, 3, minus 1, 2, and negative 2, I say -2 and write -3, there's something wrong with the brain, okay? Actually, what I was doing, I was looking ahead to the next thing, -2, 3, -2. Okay. Oops. What are we going to do with that? If we're going to try to find its inverse, what are we going to do?
We're going to write a 3 by 3 right next to it.
And what will that be?
1, 0,
1, 0, 0,
0, 1,
0, 1, 0,
0,
0, 0, 1. Okay? That's called adjoining the identity matrix to it. The old word we were using before was augmenting the matrix with the identity matrix. To me, both of those are the same. Why did come up with a new word? All right, what's the first thing we want to happen? 1 in the upper left. It's already there for us. We are so lucky, aren't we? What do we want to happen after that?
0.
Yeah, 0's below it. So how do we get that 3 to become a 0? Row 2.
Was
Okay.
no, that was minus.
-3, row 1. That should do it, right? Okay. So since we're using row 1, we're going to write it down, leave it alone for now. 1, 2, 0, 1, 0, 0. Okay? And what's our new row 2?
0,
0.
-5.
Isn't it -7? Is it -7? Ooh, that's a big boo hiss. Okay, next. Two. Okay, next. -3. Next. 1. And last, 0. All right. What's the next thing we want to happen? 0. Where the where the -2 is, a 0 there. How do we make that -2 into a 0? I'm sorry, I've got the yawnies now. I don't know why. How do we make that happen? Second? Go ahead, somebody. Row 3 plus 2 row 1. Right? All right, what does that give us for the first entry? 0. 7. Okay, I've gotten lost here. Wait. Yeah, -2. Second, 2. Is that what you said? Okay.
I got lost myself.
Okay.
So it's 0.
Okay, 0. And 1. All right. Can we do a little timeout for a moment? If you notice similarities here, at least in the first 2 entries, if you were to add these 2 rows together, which you can, that gives you 0,
0, 0.
blah, blah, blah. Guess what? If you wind up with a row of zeros here in the first part, you're never going to get the I matrix set. So as soon as you see this, you can say, stop, no inverse. This is what we call a singular matrix. Does not have an inverse. Now, there's nothing looking at it indicated it was any less invertible than the previous one, but sure enough, nope, not going to happen. So if you add these 2 rows together, you get, for the first 3 entries here, you get all zeros. That's not allowed for an identity matrix. Got to be a 0, 0, 1, not a 0, 0, 0. So that is that. Now let's see how far they went. They did go so far as adding them together, and as soon as you see it, they stop. So don't pretend that you can get anything out of that identity matrix. You can't. So don't pursue it any further. As soon as you see zeros on this side, stop. You're not going to get an inverse matrix on the other side. Okay? Just don't do it. Okay? Now, Gaussian elimination to use to find the inverse of matrix works well, even as a computer technique for matrices 3 by 3 or larger. For 2 by 2 matrices, you can use a formula for the inverse rather than Gaussian elimination. Okay? And this is sort of a problem that you run into, I'm sure, when you're writing these books. What do you do first? Okay? We started out with systems of equations and matrices. Next chapter is going to be determinants. But right now, we need to know about a determinant. So maybe we should have done chapter 3 before we did chapter 2. But then you have to explain why you're doing it anyway. So they put determinants later, but they're going to tell you what a determinant is now. Okay? Especially of a 2 by 2. Okay? If this is, a generic 2 by 2 matrix, A, B, C, D. Okay? Any old 2 by 2 matrix. Okay? Now here is the new way. I mean, you can do the other, but this is so much easier. This is invertible if its determinant is not 0. Well, what's its determinant? Okay? So the determinant is very simple. It's the difference of the cross products. AD minus BC. All you have to do. AD minus BC. Okay? If that is 0, this does not have a inverse. Okay? Say again? Yeah. Okay. But if it's not 0, it could be negative 40 million, it could be positive 2/3, or 0.1, or anything other than 0, then that has an inverse. Okay. So, that's an easy way to tell on 2 by 2. Don't even try that on a 3 by 3 or higher, because the determinants there are much harder to determine. Determinants, okay? But, not only that, don't lose the determinant. It's not just a test, it's part of the answer. Okay? Here's what the determinant is. Okay, the determinant is AD minus BC. In other words, the main diagonal, the product of the main diagonal, subtract from that the product of the other diagonal. Okay? And when you get that, that's your determinant. Okay? Now, when you get it, put 1 over that, AD minus BC, don't throw it away, put 1 over that, and multiply it by this matrix. Okay? First thing, swap the values on the main diagonal. Make that a D up here and an A down here. Okay? And then negate the other two values, minus B minus C. Okay? Now, that's A inverse. And frankly, that's easier than doing Gauss-Jordan elimination. Now, a 2 by 2, it's easy to do Gauss-Jordan elimination, but this is so much easier. okay? Because the first thing you ought to do is check to make sure you got a determinant anyway. I mean, you've got an inverse anyway, and the determinant gives that to you. If this is not 0, you have the determinant. And if it's not 0, go and put that, you just calculate it in your denominator here, and then swap the main diagonal entries, negate the two non-diagonal entries. And that's your matrix. That's some number times that. Okay? It's pretty easy. All right. So let's go to example 5. All right, to erase? All right. Here's a matrix. A. 3, -1, -2, 2. First question to you, is that invertible? How do you determine?
A times D minus.
Okay, this would be 3 times 2 is 6.
-1 times -2 is positive 2.
Okay,
So of course that's not 0, so we have
it's not 0. It's 6 minus 2 is 4, right? Okay, but don't lose the 4. What its determinant is then, its inverse is then, is 1 over 4 times what?
D. Well, and going by that is 2.
Right? And 3 will be down here.
And -1 to the right of.
Okay. Okay, this up here becomes a positive 1, that becomes a positive 2. Okay? So if you did a quarter of that, then you get 0.5, 0.25, 0.25, I'm sorry, 5. My head is clogging up, I don't know why. Goodness, I'm having trouble breathing. I'm having trouble getting my eraser to come up too. Okay. 0.5 and 0.75. Now, you could write that as fractions if you wanted to. That's okay too. But that's your inverse matrix. And notice this time it happened to turn out all positive and with all fractions. Pain in the neck, but it. And since this is a 2 by 2, even though they're fractions, let's do, in fact, I think I prefer them as fractions to decimal. 3 times 0.5, that's 3 times a half would be 3 halves, right? Right? 3 halves minus a half would be 2 halves, which is 1. That's the first entry of that identity. This one would be 3/4, right? Minus 3/4, 0. Right? This one would be -1. Plus 1, that's 0. Good. And this one would be -1/2. Positive, what's that, 6 halves. So negative, right in it. No, I'm sorry. Let's go back. We'll mess something up here. That would be a -1/2, and this would be 3/4 times 2 would be 3 halves. Yeah, 3 halves minus a half would be 2 halves. Okay. Thought the old gray cells are getting awfully confused here. Okay. So we just did the A part. Let's do the B part. B is this matrix here, 3 minus 1. That looks the same. Negative 6, 2. Okay? We want to, if possible, find the inverse of that matrix. So what's the first thing we do?
Talking about the old way or the new way?
The new way.
6 minus 6.
Second?
6 minus 6.
Okay, yeah. Right.
6 plus 6.
Okay. Take the determinant. Product of the main diagonal, 6, minus product of the anti-diagonal, which is
6 minus 6
is
0.
no determinant. Stop right there. As soon as you get a determinant of 0, you know there is no determinant, no inverse. And indeed, here's another way to tell. It's real easy with the 2 by 2. If one row is the multiple of another row, and this is negative 2 times this will give you that. So that. Now for 3 by 3, no, you can't do that or anything higher. With a 2 by 2, if the one row is a multiple of another, you know that the determinant's going to be 0. Okay. Now, if it's easier to see, if one column is a multiple of another, that's also can't happen. So 2 by 2s are pretty easy to detect. That determinant is 0, therefore this does not have an inverse. Period. Okay, goodness gracious. I don't know why. This happens about this time of morning, and I can't figure out why. Sometimes I think it's the air blowing on me, and it may be, I don't know. And other times I think I've been sitting over this and breathing the air coming out of this, and I don't know what it is, but about this time of morning, it messes me up. And by the way, they wrote them as fractions. For that first one, 1/2, 1/4, 1/2, 3/4, which actually would have been a little easier. It's harder to write, but easier to multiply, I think. Okay. Now, any questions before we move to properties of matrices? Okay. So here's some important properties of matrices. 4 matrices. Now, inverse matrices, by the way. We've already done matrices. Properties of inverse matrices. Now, first, A has to be invertible. Okay, meaning you can invert it. That last one we did, not happening. That means number 1, A has to be square, and number 2, that it can be inverted. Okay? Secondly, K is a positive integer. Okay? Third, Z is a non-zero scalar. Okay? It's a scalar. Okay. If those 3 conditions are met, then the following, now I know it's this heat coming up here, it's drying my eyes out like crazy. The following are also invertible. A inverse is also invertible. It gets you right back to being A. Okay? A to the K, remember K was some positive integer. That is also invertible, okay? Third, C times A. C was some constant, any constant, non-zero scalar. It's invertible. CA is, okay? And finally, remember what that stood for? A superscript T. Yep. A transpose. The transpose of A. which means you change the orders of rows and columns. Okay? Not the order of them, change their position. Make these rows this column. Okay? That makes these columns this row. Okay? So that's the transpose. So all four of those are invertible. And the following are true. So that's the first part. Those are invertible. If A is invertible, okay, all those things are true, then these four are invertible. All right. First, I've said this before, I think, and we'll say it again, and we'll keep saying it as long as it takes. The inverse, remember A was invertible, so it does have an inverse, A inverse. But if you take the A inverse and invert it, guess what you get? The same A you started with. So the inverse of an inverse is the original matrix. Okay? So assuming A has an inverse. Yes. All right? Now, number 2. Let's deal with the A sub k. So the A sub k, we said it was invertible. What is its inverse? Okay? Well, if you remember, A sub k to begin with is A times A times A times A, k times, right? That's what it means to be A to the k. Okay. I'm having trouble, number 1, breathing, but number 2, focusing my eyes. So that would be A to the 4th, what I have written there. Okay? Now, what would be the inverse of that A to the k? Well, from what we learned before, that was A inverse times A inverse times A inverse dot 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 times A sub k. Okay? Oh, wait. Sorry. Man. I'm sorry. I know what I'm trying to say, and I'm having trouble saying it because I keep feeling like I'm going to be sneezing. That's A sub 1, where these are k factors. K multiplied. Okay? Well, what does that become? That's A inverse to the kth power. Huh. Well, look at what that is. A to the k inverse is A inverse raised to the kth power. Okay? Huh. Interesting. Okay? So that's that one. Number 3. Let's go to C sub k. All right. You said it was invertible, so CA, I said CK, CA, the inverse of that is, anyone want to make a guess? One over C has A to the inverse. Okay? So when you multiply a scalar times a matrix, remember that means every element is multiplied by that same scalar. Okay? But then you invert that matrix that we already told us was invertible. What it does is, does 1 over C times the inverse of that matrix A. We started with matrix A without the C, and you know it was invertible, so it has an inverse. Then C times A, the inverse of that is 1 over C times A inverse, which is sort of interesting. Maybe not expected, but not surprising. Okay. Number 4. Let's do the last one. A transpose. What is its inverse? It's said up there it has one. What is it? Well, sorry. A lot like what we did with the multiples, we're going to do here too. That would be A inverse transposed. Okay? So if you know A has an inverse, and you certainly know how to get the transpose of A, without having to go back and redo anything, you can, if you know A has the inverse and what it is, just transpose the inverse and you've got, well, relation to what you started with. That's what you get, A inverse. All right. Sorry, I need to clear my head. And maybe this is as good a place as any. There is a proof here given, I'm sorry. And they're pretty nifty little proofs. I think it just does maybe one of them or more than one. I think it does 1 and 3 and leaves properties 2 and 4 for you to prove. They're in exercises coming up, and you certainly can do that if you wanted to. That second one up there, it actually using almost the same idea here, but writing the first part a little differently, A to the minus K. Okay? Now, be careful with that. Don't try to read into this what that would mean in real numbers. Okay? Because that's not the same thing. But that really looks like that's what that's describing. And A to the minus K is exactly the same as what you're describing there. So that's another, for non-singular matrices, you can do that. Of course, if you have a singular matrix, don't mess with it. Don't try to undo it. Okay. Now, it says using that convention, you can show something else, and do all this in the little print here. It seems like this should be a little more important. But I think we did this earlier. Seems like we did. If you have A to the J, multiplying that by A to the K, that's the same as doing A to the J plus K. And A to the J raised to the kth power what would you expect that to be, you know, if you were what would be your expectations of that? That's an ugly J. Dot sort of got wandered down into the yacht. Okay, I did too much. There's a dot. If you extended from whole numbers, extended the same apparent value to it, what would you expect this to be? A to the J times K. You're absolutely right. Okay? And that's true for any integers. Notice they don't say positive integers. Any integers, J and K. All right. Now, all right to erase? Okay. can we take just a short break? I just need to go and clear my head because I'm having trouble breathing. We'll come back and do the discovery there at the bottom of the page recorder. All right, A is this little matrix here, 1, 2, 1, 3. B is this little matrix here, 2, -1, 1, -1. Okay. It says calculate AB inverse. Well, let's first calculate AB. What would AB be? First, can you even multiply A times B? Okay, what size will it be? 2 by 2. Okay, now there's no shortcuts to multiplying, you have to just multiply. So what would be the 1, 1 entry? Four. Perfect. All right. The 1, 2 entry. Okay. It doesn't matter which one, whichever one you want to. I was going to do the 1, 2, which is first row, second column. That would be.
That would be -1.
That would be -3. Okay. -3. The 2, 1 entry would be. Five. Okay. That's what I got too, but now when I look at it this way, I don't see it. 2, 1. Yeah. Yeah. Got it. And the 2, 2 entry would be -4. Okay. The next thing it said to do, in fact, it was the first thing it said to do, is find AB inverse. Okay? Now, how do you find the inverse of this matrix? Find the determinant, first thing. What would that be? -16. -1. The determinant's -1, so it doesn't have an inverse. Yes, it does. How do you get it? Be -1 over -1, which is just negative. And then, what do we do next? Okay, now you switch those. Yeah, you do the -4 here and the 4 down there, and then that would be a -5 down here and a 3 here, right? You don't move them, you just negate them, right? Now, let's multiply the minus sign through and see what we get. Yeah.
You just flip everything? It flips all the signs?
Yeah, it changes every sign, exactly. So that'll be 4, -3, 5, -4. Which, do you notice anything? That is AB. So in this case, AB is its own inverse. That's like my, what was it? It's an old, I think, country and western song. My son was my own grandpa, or something like that. It's just talking about mixed up family trees, you know. Kind of crazy. That's sort of amazing. Let's try some other things. Let's do A inverse. What would A inverse be? What would be the first thing you do to get A inverse? And what would that be? 1, okay. So that was pretty easy. So then what do you do? Okay, I can do that. Okay. And what else do you do?
Fill in your box.
Yeah, what goes where?
You want to switch A and B. So that you switch 1 and 3.
Okay, so make that 3 and 1 there.
B and C are just negated.
It's what? Negate those two. -2 and -1. Okay, so there's your A inverse. That's not the same as A. Okay, that's good. They also said do B inverse. What's B inverse? And what is that? -1. So I'm just going to put the minus out front. You don't change the signs on those. -1, 2, you just change the positions. The other two, you change the signs. 1 and -1. Okay. Now, when you change the minus sign here because of the minus out front, and what would that be? Okay, so there you have B inverse. Okay, now the next thing it wants us to do is do A inverse times B inverse. Okay, so we'll do that on the next line if we got room. A inverse, B inverse. Okay, can we even multiply those two? Yes. What size will it be? 2 by 2. Okay, and let's see what we've got. So this one times the last one there.
That'll be 1.
1, okay. 3 minus 2 is 1. The 1, 2 entry, the first row, second column. Is it -1? It would be a -3 plus 4, right? 1, wouldn't it be? Okay. So 1, 1. Okay, 2, 1 entry would be zero. And 2, 2 entry would be
Zero.
really?
Maybe not.
-1 times -1 is 1. Plus 1 times -2 is -2. 1 minus 2 is -1. Isn't it? Okay, -1. Okay, I don't see anything really all that exciting about that. But let's do B inverse A inverse. Now it seems like something rings a bell for me. You can also do this. It'll be a 2 by 2. Now, got to reverse your order here. Would it help to write A inverse on the other side of B inverse? Would that help you do it?
I think I can still do it. Well, I'll do it.
It's doing across this way and down that way. So that would be, the 1 entry would be 3 plus 1, right? Or would it be helpful to write the A over that? A inverse over that. Up to you, whatever makes you feel good, okay?
I'm going to try to do it without.
Okay, so it would be going across there and down here. So 3 plus 1 is 4, okay? Okay, the 1, 2 entry would be row 1 of B, column 2 of A. And that would be -2 minus 1 is -3. Is that what you said? Mm-hmm. Okay, -3. I can't hear well. Okay, the 1, 2 entry would be, 2, 1 entry would be second row of B inverse, first column here. That would be 3 plus 2 is 5. And the 2, 2 entry would be second row of B, second column of A. -2 minus 2 is -4, right? Now, hopefully this comes as no shock that the AB inverse is B inverse A inverse. I think we did that before. And sure enough, those are the same. But remember, for some reason in this case, it's also the same as AB. That's not going to be in all cases, but this happens to be the same here. Okay? Now, the second part here says, make a conjecture about the inverse of a product of two non-singular matrices. The inverse of a product of two non-singular matrices. Number one, we know it is a non-singular matrix itself. Okay? I don't know if these are supposed to represent any two, but the one we did gave us the same matrix again. I don't think that's always the case. It says select two other non-singular matrices and see whether our conjecture holds. That sounds like something for the student, doesn't it? Okay, we're not going to take class time to do it. But it's sort of interesting. All right, let's go on to example 6. Okay. It says compute a to the -2 in two different ways and show that results are equal. All right. Here's a. That's 1, 1, 2, 4. Okay. And here's what they're asked to compute, a to the -2. Okay, it says compute that two different ways. Now, how might you compute it one way? Okay, what I hear you to say would be a inverse squared. Is that what you're suggesting? So let's first do a inverse. All right. Can you do it? It's a square matrix, so at least you can try. So what would be your first step? And what's your determinant? 2. So you know the coefficient out here is going to be 1/2. Okay, 1 over 2. 1 over your determinant. Okay, and then what do you put in the box?
Switch A and D, so you get 4 and 1.
4, 1.
And opposite sides for B, and so you get a -1
negative 1, and negative 2. Okay, now multiply by 1/2, and what do you get? 2.
Negative 1/2, negative 1, and 1/2.
Got it. There's the inverse. Okay? Now, to square that, we multiply it by itself. 2, negative 1/2, negative 1, 1/2. Can you do that? Sure, it'll give you a 2 by 2. So let's do it. Do it to it. The 1, 1 entry will be the first row here, first column there. What will that give you?
The first one is
First row here, first column there. 4. Okay.
4 plus 1/2.
Got it. And I would call that 9/2, right? Let's call it 9/2. Okay. The 1, 2 entry would be first row, second column. And that would be first row, second column.
3/2.
Okay. Well, then 2 times negative 1/2 would be negative 1, right?
Correct.
Okay. And then this times that would be negative 1/4. So it would be a negative 1, negative 1/4 is negative 5/4. Is that what you said? Negative 5/4. Okay. 2, 1 entry. Second row, first column.
It'll be a negative 5/2.
Okay. That would be a negative 2. That and negative 1/2. You're absolutely right. Negative 5/2. Okay, and the 2, 2 entry. Second row, second column.
It'll be 3/4.
3/4. 1/2 plus 1/4 is 3/4. Okay, we did it one way. What is the second way we could have done that?
Switch.
Yeah, a squared, and then take the inverse of that, right? Okay, so let's do a squared. That would be a times a. 1, 1, 2, 4 times 1, 1, 2, 4. You certainly can do that. That gives you a square matrix, 2 by 2. And what would be the first entry there?
Plus 1 plus 2 is
3. Okay. The 1, 2 entry.
1 plus 4 is 5.
Okay.
1 plus
Okay. The 2, 2, the 2, 1 entry
2 plus 8
is
10.
10. And the 2, 2 entry would be
2 plus 16.
yeah, 18. Goodness gracious. Okay, so that's the a squared. Let's take the inverse of that. And what do you, what you gonna do first? I was liking this problem up until this point. What's the inverse? I mean, what do you do first on the inverse? Determinant, and what is that? Is 54 minus, which is 4. So your inverse would start off with 1 over 4. And then what do you do? Yep. What goes where? Okay, so that would be an 18 here and a 3 down there. A -5 where it sits and a -10 where that's at. Okay, and now what I have to do is multiply. 1/4 times 18 would be 9 times 1/2, right? So that would be 9/2 minus 5 over 4 and 1/4 times a -10 would be 1/2 times a -5. So it would be -5/2, and then that would be a 3/4, and bing, 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 bing. Looky there. They're the same. They should be. Okay? Now, which of those are easier? Even though we got some pretty big numbers here, you dealt strictly with whole numbers until the very last step in that one. And to me, that was a little easier than multiplying all these fractions and adding and stuff. So, I don't know. Pay your money, take your choice, whatever you like best. You've already paid your money, so take your choice. Okay. So, we've done it both ways and got the same answer both ways. Okay. Now, let's mark theorem. Anyone need that up there a little longer? Okay. All right. Theorem 2.9, inverse of a product. Okay? And this is what we just were seeing earlier, and indeed it's true. Okay? A and B both have to be invertible matrices. What does that tell you about it? Oh, and of order n. What does that mean? Invertible matrices of order n. Okay? First and foremost, they both got to be squared. Now, I don't know if y'all recognize my symbol here for a square. It's not a very pretty square, but I remember it from my youth because my younger brother was a bit on the wild side, and I never was. He found me totally boring. So guess what name he gave me? L7.
Oh.
L7, of course, from your perspective, it would be like this or something. And that meant a square, okay? And so from then on, in fact, to this day, sometimes you say, hey, L, he just leaves off the 7 part, not even thinking about where he got that from. I'm L to him. So that's why I do my squares of that. First, they've got to both be square matrices. And to do what we're going to do, they've got to be the same size. So the order n means n by n. They're both n by n matrices, and they're both invertible. So that's what we have to begin with. Okay? Then AB is also invertible. Okay? Well, certainly if they're both n by n matrices, you can multiply them together, and the product will be an n by n matrix. Okay? Right? Okay? Now this says that AB is also, the product is also going to be invertible. We saw that in the last discovery, at least for one of them. And then here's the second part, that the inverse of AB, we said it's invertible, the inverse of AB is going to be B inverse times A inverse. Okay? Now I kept saying we've seen that before, and I realized, no, we haven't. We did it with transposes. The transpose of a product is the product of the transposes, but in opposite order. Same thing holds for inverses. The inverse of a product is the product of the inverses, but in different order, in the reverse order. Okay? Now, and it's actually a pretty clever little proof to show that it's indeed true, that these two are inverses of each order, of each other, that they are the same. Let's see how to say that. That the inverse of AB is equal to inverse B times inverse A. Okay? Well, if that's true, that means that well, you know that AB times AB inverse has to be the identity matrix, right? A matrix times its inverse has to be the identity matrix. And these are both invertible matrices, so that's true. So, since we're claiming that's what the inverse is, that means AB times B inverse, A inverse, had better also be the identity matrix, hadn't it? Okay? Well, looky here. Change your order, and you can do this, because these are all square matrices same size, as A times B inverse times A inverse, right? We're just gathering the middle two. Doing those first, right? And then doing these on the end. What is B times B inverse? It's I, because B is invertible. So that's going to be I, right? So this is going to be the identity matrix, I sub n, right? And what is A times I sub n? No, it's going to be A. Multiply 7 by 1, you get 7. Multiply a matrix by the identity, you get the matrix. And then what's A times A inverse? That also is going to be I n. So, yep, they must be inverses of each other, because when you multiply them together, you get the identity matrix. Okay. Pretty clever little proof. And a lot of the proofs in linear algebra, especially with matrices, are going to be that kind of thing. You almost feel like you're running around in a circle, but you really are going in one direction. Okay. Okay. Let's see if we can get example 7 done before we run out of time. Okay. Here's a matrix. A. 1, 3, 3. 1, 4, 3. 1, 3, 4. Here's a matrix B. Sorry. 1, 2, 3. 1, 3, 3. 2, 4, 3. Sorry. Now, I'm glad they're not having us do this, because if it would take more time than we have, they're telling us what the inverse is. 7, negative 3, negative 3, negative 1, 1, 0, and negative 1, 0, 1. Thanks for telling us that. Not only that, they told us what B inverse was. Thank you very much. Okay? And this is 1, negative 2, 1, and negative 1, 1, 0, and 2/3, 0, negative 1/3. All right, thank you so much for doing all that work for us. Okay? Now, it says using theorem 2.9 produces that the A times B inverse, okay, equals B inverse A inverse, okay? So, rather than multiplying A times B and then finding the inverse, let's just do B inverse times A inverse. That's a much easier process, right? And the theorem tells us we can. So let's take B inverse and multiply it by A inverse. This time I'm going to write it over here. 7, -3, -3, -1, 1, 0, and -1, 0, 1. Okay? And sure enough, if we multiply those two together, we're going to get a 3 by 3. Okay? And let's do the multiplication as quickly as we can. 1, 1 entry. 7 plus 2 is 9. Minus 1 is 8, right? Okay. 1, 2 entry. -3. That would be -5. That's a -5, right? Okay. 1, 3 entry. -3 plus 0 is -3. Plus 1 is -2. Okay. 2, 1 entry. Second row, first column. -7. -8. Plus 0 is -8. Whew. 2, 2 entry. Second row, second column. 4, plus 0 is 4. 3, 2, 2, 3 entry. Second row, third column.
5.
No, I think
That's
it's
a
3. Yeah, 3.
0.
That's just a 3. All right. 3, 1 entry. Third row, first column. Oops. Ooh. It's what?
Is that a fraction?
Yeah, that's a fraction, 2/3. Do this, right?
That's
14 thirds,
14.
okay, plus,
0.
okay, plus 1/3.
1/3.
That would be
15.
15 thirds, which is 5. Okay, that worked out nicely. Okay, the 3, 2 entry.
6 over 3.
6 over is a -6/3, which is
2.
-2. 2.
0.
So what do you say, -2? And the last, 3, 3 entry. Third row, third column.
10 over -6 over 3. 6
Yeah.
over 3.
It's -2, right?
Uh-huh.
Okay, -2 plus 0 minus 1/3. That would be minus 2 1/3, which is minus 7/3, right? Minus 7/3. Oh, I thought we were going to get by with no fractions. But fractions are numbers. Okay. And sure enough, look at what they got in the book. It looks like identically the same thing. Now, does that mean that it's easier to multiply the inverses of the two? It is when they give them to you, okay? But in reality, if we'd had to start from here, we'd have had to find this inverse, find that inverse, and then multiply them in that order to get this. Whereas the other one would multiply these two together and then find that inverse. This is finding two inverse and then one product. This is one product and one inverse. Generally, it's easier to do it that way. But since they gave us the inverses, we didn't have to find those on our own. Okay, I think we may be out of, we're past out of time. Let's see how far, okay. We'll start next time with Theorem 210. Okay. Oh, we came close to finishing the section, but didn't quite. Do any of the odds 1 through 5? This is on page 71 and following. Do any of the odds 7 through 29? Do any of the odds 31 to 35? Do either 37 or 39. We did some just like the 2 by 2 there, are very similar. And do any of the odds 41, either 41 or 43. Now it says do the transpose. I don't think we did that yet, did we? Yeah, we did. We had that. So either 41 or 43 or both. And I think the next part we didn't quite do. So stop there at 43. We'll pick up the rest of those later. Good deal. All right. Any questions? Okay. I don't know what I'm doing here. That's what I meant to do. Okay.